Okay, hello people. This is segment number 4. I assume that you have watched the first 3 segments and therefore you are reasonably familiar with shell modeling and the 2 methods of doing it. Either extract the surface or if necessary, create the surface directly in wireframe and surface design. Okay, I'm going to move to chapter 11, and the reason is that we would like to create a shell model where the horizontal surface has a different thickness than the vertical surface as you see here. The side ring is clamped and the horizontal ring is being pushed down by a given force. Well, first of all, I'm going to ignore all the dimensions when I make this thing model, but the first approach is going to be creating a solid object like that and then extracting the top and the vertical faces. So you end up with your bracket like so. The only thing is that you cannot join these two because these two surfaces have different thicknesses. If you join them and eventually give it a thickness, it's going to use the same thickness for both pieces. Okay? So let me go ahead in Catia, and ignoring all dimensions, we're going to create the model as I described it. Let's start with the part file. There we are. Okay. So on the horizontal plane, I will sketch a nice centered rectangle like that. Again, ignoring dimensions, and then I can drill a hole here. I can make a circle here so that eventually it will turn into a hole. Exit and pocket it to the height that I want. So let's make this 2. Then on the side face, I will sketch a circle. Assuming this is all centered and everything, I'll let you worry about those things. And then make a pocket all the way to the end. Yeah, to the last. Okay, that's fine. So here we go. All right. Now we go. To wireframe and surface design and extract these 2 faces. So you go to mechanical design, third workbench from the bottom, and extract. You know where it is. Extract the top face and extract the side face. Okay, do not join them. Let's apply material on this thing. Let's make it out of aluminum. All right, good. So we are done. Now keep in mind that there is a solid object here. If you do it like this, the minute you go through the generative structure analysis, Catia will mesh this solid object. And we don't want that. So you have to delete that mesh, the 3D mesh, and delete the 3D property. So let's go to generative structure analysis. Say OK. And you can see that the solid is there and it has been meshed. So right away you go to the 3D mesh you deleted and the corresponding 3D property you deleted. Okay, I don't need this solid object, so I can put it in hiding. I cannot delete it because the surfaces are coming from that. Also notice that if I'm asked to use full symmetry, I need to cut this thing. I don't think this was actually, symmetry was used in the book, so I'm not going to cut it here, but when I do it the second way, using the direct approach in the wireframe and surface design, then I'm going to cut it, okay? So I am not using plane of symmetry on the test. You will be asked to use all planes of symmetry if applicable. In this case, the YZ is the plane of symmetry. So you have to cut it like that and put the appropriate boundary curve or appropriate restraint on it. Now remember, just cutting it is not going to cut it. You have to put the appropriate restraints on those imaginary edges that you create. But since I want to be in line with what's done in the book, at least for this try, I'm not going to cut it. All right, now first thing we need to do is to mesh these. Okay, so in the using the shell mesh, I select the top and notice that it no longer will no longer, at least this is not a mesh on the vertical face. In fact, if I displayed the mesh, it only does the top one. Okay, so let's deactivate one. So you have to do this thing one more time for the vertical edge, which is right here. Now, if you say, show me the mesh, it'll show you both of them. However, these guys are not talking to each other. So let's deactivate this one more time. Okay, good. And now we can put different shelf thicknesses on these two pieces. So here's the 2D property. On that, let's say it's 0.1. And on the vertical face, we can put a different thickness. So for example, I'm making it 0.2. You see, there's a 0.1 here, and there's a 0.2 there. All right. What do we know here as far as the restraint? You were told that this edge is clamped. Okay, there it is. And you are told that a force of 100 pounds, whatever, these numbers are ridiculous because I don't even know what the size of this shell is. 100 pounds on this circular arc. So you apply force, distributed force on this circle, downward 100 pounds. Okay, good, good. The only thing is that if I run this, it will bomb out. The reason is that these two faces are not connected. It's like if you put a force on that sheet and that sheet is not connected to anything, it's going to move as a rigid body. In fact, if you don't believe it, let's run it and see what happens. Just to say it bombs out, and if you plot the deformation, you can see what happens. It moves as a rigid body, all right? So let's deactivate this last plot that we made and go and try to fix this. All right. Now, what I'm going to do is I'm going to tell the edge, the top edge, or the edge from the top surface, and the edge from the vertical surface, that these are related together. Remember the analysis connection? First, you declare them that they're related to each other. So general analysis connection, and you can put the cursor. Notice that there's a little arrow pointing to the right. That means the edge that that index finger is on it belongs to the top surface. And for the second component, now you put the cursor close to the line and the arrow points down. That means the edge that I'm picking now is belonging to the vertical face. Okay, this connection is created here. You have already seen connection in the context of assembly. And this is going to be fastened. In the book, I'm making this thing a rigid connection. That is not a good idea, although it will run, it will give you numbers, but the assumption that they're fastened is more reasonable. So fasten connection, or in the open face-to-face connection property, the fasten is the third one from the left, and this connection is fastened. Notice that it puts the fastener sign here. And now let us run this thing. And it will work. So if you look at the deflection, notice that it tries to show you deflection, except that the scale was changed. So let's put it on the default, and you can see that it's actually deflecting. There is also deformation in the vertical face, but they're so much smaller compared to the horizontal face that you can't even see it, okay? So just the fact that you see this vertical face is staying put, although if you put it from the side and change your amplification factor to something bigger, so about 3 or 4, 5, you can see that it is actually bending. This guy is actually bending too. Right there. You can see that the vertical face is also moving. Now, I'm going to repeat the same problem with wireframe and surface design without actually creating the solid object. So let me kill this, kill that, start a part file, Okay, so on the vertical plane, I will sketch a line. Just be patient here because these steps may look ridiculous to you, but there's a reason behind it. So here's a line. Exit and extrude it. Let's say by, I don't know, 2 inches. So this is my vertical face, vertical surface. And because of what I did, it's actually a surface. And when I do the horizontal one, they don't talk to each other. That's why you can put different thicknesses on it. So on this horizontal plane, I will draw, where is this? I will draw a line that is like that, exit, and extrude it. This way of doing it, let me actually make this thing shorter. Not that it matters, but I would like to make it shorter so that you get the same feeling that you had for the other thing. All right, so what we're going to do is we're going to extrude that in the other direction by the same length. I don't remember what this thing was, but let me yeah, I don't remember what this thing was to fix this. We say okay, so I'm going to go to this geometry about this first sketch and make this thing 2 inches so that eventually they will match. I think if I make this thing 2 inches, they will actually match. That should not bother you. I'm just explaining what needs to be done. Okay, good. So these two surfaces don't talk to each other because the extrusion was done of a vertical line and the horizontal line. And do not join them. Let's hide this line in the middle, which came from one of the sketches. All right, good. Now we're going to, on this face, we will sketch. Remember, in this problem, I want to use planes of symmetry, okay? You should have used it in the other one too, but I decided not to worry about it because of the way it was done. So top line, control bottom line, control the center. Let's make it symmetric or equidistant. Exit. And then on this vertical face, we draw, fit this, the circle. This is the circle that's going to get clamped eventually. Top line, control bottom line. Excuse me. Control the center of the circle. Let's make it equidistant. What did I do here? Top line, control bottom line, control the center, equidistant. And if necessary, if you want to center it, you can also center it vertical line, the other vertical line center. I'll leave it like this. I'm sure it's going to be centered here. Good. Now what we need to do is to cut a hole up there. So you go to the saw. Remember your environment frame and surface design. You go to the saw, not the trim, the saw. Read this thing carefully. It says the element to cut is this face, and the cutting element is that. So we're going to cut it. Now go repeat it again. The saw. Cutting element to cut is this, and the cutting element is that circle. There it is. Finally, I want to cut this thing exactly halfway in the middle. Oh, I noticed that I don't have a plane halfway in the middle, so the easiest way may be to create a plane halfway and then use that as a cutting. So we can say offset from a plane, from this vertical plane, by 2 inches in the other direction, because by 1 inch in the other direction. Right, this plane is going to be right in the middle. Okay, and now I can saw it. Saw this with that plane, and saw this with that plane, and there it is. This is half of the model because it has one plane of symmetry. So let me hide these sketches, which we don't need. I mean, actually, they're not going to participate in finite elements. Okay? And also this one. How about this? Hide it. All right. So, did I apply material? No. Let's go apply material. Apply material made out of aluminum on the part. Say OK. Good. We now go to generative structural analysis. It's the same geometries, different orientation right there. Okay. And we don't have solid elements because this was created directly. And let us mesh both of these. These are going to be separately meshed because they're not joined. So this is meshed. It's too big. So let's make it 0.2. That's more respectable. And repeat it. Again, mesh the vertical one. That's good. Let's put thicknesses on them. So 2D property on the top one, which was 0.1. And once again on the vertical one, which is 0.2. You can display the mesh if you want. It's just that if you want to see it, you have to display it. I don't want to see it, so I'm going to deactivate this. All right. Now, what do we have? We have that circuit half an arc is clamped. And I have a force of 100 pounds divided by 2. Remember, when it was the whole circle, I told you to put 100 pounds on it. Now, this is half a circle, so force on this face, on this edge, in the proper direction. Because of the way it did things, the direction has changed. So it's going to be minus 50, not 100. It's half of what you put on the actual model in the downward direction. And there it is. See this? This is going to be put on that entire face as distributed load. We now have planes of symmetry here. So we have to do user-defined restraint, uncheck all of these. This edge and that edge lies in the plane of symmetry, which is, pay attention to the compass, it's XY plane, so it does not move in the direction Z and opposite for rotation. And now we have to do these vertical edges. These vertical edges are also planes of symmetry. So uncheck all of these and pick them. So you have this one and that one, and based on my coordinate system, that's still XY. Therefore, no displacement in Z, and rotations are opposite. I could have done both of all these 4 lines at the same time because they're in the same plane of symmetry. Good, good. Finally, if I run this thing, it's going to bomb out because these 2 pieces are not talking to each other. What I showed you in the previous method, which was surface extraction, I created the connection between the edge here and the edge below and made that fasten. I also want to point out to you, this I could have done as connection between the top face and the bottom face and make it connection, make it a fastened connection. The thing that's done in the book as a rigid, it's not a good idea because it's not very realistic. Although it will work and give you color and numbers and things like that, but you know, I mean, it's just not right. This time, just to make it different from my first attempt, I'm going to create between this face and for the second component that face instead of the edges that we did in the first approach, and then we make this thing a fastened connection. Where is this fastened connection? Right there. On that, here's your fastener. As you see, now if I run it, it will work, and the numbers are going to be the same thing that we had before. There, you can see that. There it is. Did I put the force in the wrong direction? I'm not sure. I'll check it. Oh yeah, because of the orientation that I have for my compass. See the compass? The force should have been in the positive y direction. It just happened that I changed stuff so that my orientation has changed. So the more appropriate load was here is plus 50 pounds because it is in the direction actually of y, positive y. So let's run it again. And now look at your deformation, and it goes down as you expected. Finally, let's see, what did I want to show you here? Yeah, that's pretty much it. So you found out that if you join surfaces, the thickness will end up to be the same. If you don't join them, then somehow you have to ask them to talk to each other, and this was the process. In the first run, I made edge-to-edge connection and made that fasten. Then I showed you face-to-face connection, the horizontal sheet and the vertical sheet connection, and then fasten them. Also remember that we could have done this problem as an assembly. So basically, we have two parts. You could have, although I did it all in a single part, but I could have created the top face as a part, the bottom face as a part, assembled it together, and done it as an assembly, which you have already done, except that you haven't done shells, but it's exactly the same concept. I suggest that you try it. And then you have to create a connection between those two edges or those two faces and make it a fastened connection. So it's nothing different from what